Welcome to the DX Today podcast, where you get facts and no hype. Today, we are strapping in for what might be the most crucial architectural conversation happening in technology right now. For the last few years, the big story in AI was size, how many parameters, how big the data set. We had these massive, static, monolithic models like ancient oracles just waiting patiently for a prompt, spitting out text, and then waiting for us to tell them what to do next. But that era, that passive reactive era of just text generation is definitively over.
Yeah.
We are now in the age of agentic AI. And this isn't just a new feature, it's a phase transition.
That's precisely right. The shift isn't just an incremental update to a model's intelligence. It is a full phase change in how we conceive, build, and deploy intelligence systems in the enterprise. Previously, LLMs were passive text generators. They were high-powered tools you operated by hand, step by step. You had to copy the output, review it, and then paste it into the next tool. Agentic AI, by definition, possesses what we call goal-directed autonomy. It is a proactive system. You assign it a high-level, complex, and often multi-step command, something like refactor this entire legacy code base to use the new security library.
Wow.
Or audit all our Q3 financial statements, identify anomalies, and generate a variance report.
Yeah.
The agent doesn't stop there. It figures out the necessary steps, allocates resources, executes actions in the real world using digital tools, and iterates until that high-level objective is met.
That distinction, the move from passive oracle to goal-directed autonomy, that's everything. It means we aren't just getting text outputs anymore, we're getting system mutations.
Right.
The agent is writing and deploying code, submitting financial transactions, changing database entries. It's operating in our production environment. So before we dive into the deep end, let's unpack that autonomy. What does that architecture even look like? How does a piece of software achieve this kind of self-directed action?
The sources are pretty consistent on this. They break down the agentic architecture into 4 core capabilities, and they form a continuous self-correcting loop.
Okay.
First, the agent needs to know what's going on, which is perception. The agent has to be able to read the state of its environment. That could mean querying a database, parsing a code repository, reading a knowledge-based document, or integrating a real-time feed from a Slack channel or a Jira queue. It perceives the world's current state.
So once it has the state, it has to figure out what to do next.
That leads to the second capability, reasoning. The agent must evaluate that perceived state against the high-level goal it was assigned. It plans, it hypothesizes, it evaluates multiple pathways, and decides on the single best action to move closer to the goal.
And then it acts.
Third is action. This is the critical external step. It uses tools, APIs, CLI commands, function calls, SQL queries to actually mutate the environment. If the goal is refactor the code, the action is literally writing and committing the new code. If the goal is process invoices, the action might be initiating a payment API call.
And if it acts badly, if the environment doesn't reflect the desired outcome, how does it know? Is the fourth part just logging the result, or is it more of an active, goal-directed assessment?
It's the latter, and it's the real game changer, the constant feedback loop. The agent observes the result of its action. That's perception, again, measures that result against the goal, which is reasoning, and then self-corrects based on any deviation.
Like a failed API call or something.
A failed API call, a compilation error, a data mismatch, anything. And then it iterates the entire cycle again. It is constantly looping. Perceive, reason, act, observe. This iterative nature is what makes it an agentic system. The LLM is the brain, yes, but the agent is the entire autonomous body operating in the world.
That vision promises pure, unadulterated productivity, moving us past the bottleneck of human intervention for all this routine cognitive work. But when you introduce that kind of autonomy, you introduce an entirely new class of risk. If these systems can mutate the environment, what is the core problem statement we are tackling today? Why are engineering teams moving from, excitement to a lot of caution?
The core problem is fundamental, and it's mathematical. We're moving from a linear risk profile to a geometric risk profile.
Okay, break that down.
When you had a monolithic LLM, one prompt led to one output. If it failed, you got one hallucination, one bad line of text. The risk was contained, predictable, and linear 1 + 1 = 2. Now, risk is a geometric function of agent interaction, not just the model's inherent size or quality. So the mission of this deep dive is to unpack the terrifying math behind why simply scaling up AI competence by adding more agents or chaining tasks together can lead to catastrophic systemic failure. We have the data and the frameworks now to manage this, but first we have to understand the geometric danger we just introduced.
Okay, let's start with the big picture then. The urgency. Why is this transition to agentic AI happening right now? The capability has always been lurking, but this sudden wholesale adoption implies a really strong economic imperative is driving this change.
Oh, the pressure is relentless, and it comes down to efficiency and latency. Enterprises are desperate to move humans entirely out of the loop of these routine, high-latency cognitive tasks.
Right.
We're talking about automating workflows that currently require a human to coordinate across, say, 5 different software applications, waiting for one step to finish before manually kicking off the next one. And the sources highlight that this isn't some far-off future gazing anymore. It is the immediate roadmap for the next few years. Gartner's projections are they're eye-opening. By 2028, a staggering 33% of all enterprise software applications will include agentic AI components.
A third.
A third. Think of your ERP, your CRM, your internal tooling. 1/3 of them will have autonomous workers inside.
And the really chilling part of that forecast is the decision-making autonomy.
Yes. Critically, Gartner predicts that at least 15% of day-to-day work decisions will be made autonomously by these agents, without requiring human approval or validation.
Wow.
This means the systems aren't just writing drafts. They're executing complex, high-stakes workflows, planning global supply chains, autonomously refactoring legacy code bases, initiating automated trading sequences, and performing extensive financial audits, all without continuous human babysitting. That necessity for speed and scale is why the transition is accelerating so rapidly.
That forecast is huge, and it means these systems are going to be interacting with core business infrastructure constantly. We detailed the 4 capabilities: perception, reasoning, action, feedback loop. But how does combining these capabilities, especially across multiple agents, fundamentally change the nature of failure? This brings us back to that geometric risk regime you mentioned.
This is the moment where traditional engineering intuition just breaks down. In the old world, systems were largely deterministic. If you wrote a function that added 2 numbers, it always added those 2 numbers, or it threw a clear deterministic error. LLM-powered agents are stochastic and probabilistic. They generate the most likely next token, not the mathematically certain next token. They are not 100% reliable. They are R% reliable, where R is always less than 1.
And when you chain those stochastic systems together, the unreliability multiplies.
Exactly. When Agent A produces an output, that output is immediately passed to Agent B as its new input. This is the crucial distinction. In a monolithic system, an error was contained. In a multi-agent system, an error is now the certified input and foundation for the next stage of work.
Oh, wow.
An initial flaw or a minor misunderstanding in the first step gets baked into the entire chain of logic and is treated as gospel truth by every downstream agent.
Wait, so if the agents are highly reliable, say 95% reliable, why should we panic? That sounds pretty good. Why does that small 5% failure snowball so fast?
Because of the geometric function of risk. Let's look at the formula the sources emphasize, which is the mathematical representation of this problem. If a single agent has reliability R, let's say R is 0.95 or 95% accuracy, a chain of n independent agents attempting to complete a task has a system reliability that scales roughly as R to the power of n.
R to the n.
I remember enough math to know that if R is anything less than 1, and in stochastic LLMs R is always less than 1, never 100%, then as n, the number of agents or steps increases. R to the power of n approaches 0 extremely fast.
That's terrifying.
That is the terror of the geometric profile.
Okay, let's ground that terrifying calculation in a real-world scenario. Let's imagine we task an agent system with performing a complex financial audit that requires, 20 distinct sequential non-trivial steps, so n equals 20. If we are running highly reliable agents, say 95% reliable, R is 0.95. What is our system reliability?
The calculation is 0.95 to the power of 20. And that result is only about 36%.
36%.
Think about that magnitude. Your individual components were deemed high quality, 95% reliable. But because of the necessary sequential chaining, your system reliability is suddenly less than 2/5. That complex task, which worked perfectly in a small demo, now fails almost 2/3 of the time in production. That 36% reliability is the kind of finding that keeps chief risk officers awake at night.
And the source material points out that our existing observability tools are totally blind to this specific type of cascading failure.
They're completely inadequate. Traditional observability tools were designed for linear logs and deterministic pre-programmed failures. They monitor things like latency, CPU usage, and standard HTTP response codes.
Right, the usual suspects.
The usuals. When Agent A misinterprets a revenue variable, say 50 million instead of 500 million, and Agent B uses that flawed input to successfully call the ledger API, the system reports a 200 OK status code for both API calls. The metric looks green. The system appears healthy.
But it's not.
But internally, the agents are confidently hallucinating a massive financial collapse, or they're refactoring the wrong part of the code base, or they are launching a product based on flawed market data. The catastrophic error, what we call semantic drift, is buried deep in the interagent context and logic flow. The output is internally coherent to the agents, but externally catastrophic to the business.
Wow.
So we need to move past simple logging and adopt sophisticated agentic engineering to manage this hidden geometric risk.
That transition from linear to geometric risk is a powerful and necessary warning. But here's where the engineering consensus hits a wall. For years, the mantra was simple. If you want better AI, just add more models, add more data, make the system bigger. We just assume a hive mind of agents working together must naturally be better than a single agent. What does the quantitative research say about that naive assumption?
The research says the assumption is fundamentally and provably wrong, and the data is brutal for that prevailing mindset. We are learning that agent systems do not scale like neural networks. They scale like bureaucratic organizations, complete with coordination costs, communication bottlenecks, and inherent inefficiency.
Ouch.
Yeah. The landmark 2025 study towards a science of scaling agent systems, conducted by Google and MIT, stress-tested 180 distinct agent architectures across diverse, complex cognitive domains. They found a hard limit on the utility of collaboration.
Let's dive right into their most critical finding, the one that redefines agent architecture, the 45% threshold.
This is the absolute inflection point engineers need to understand. The study revealed that multi-agent coordination yields diminishing or critically negative returns once the single-agent baseline performance exceeds an accuracy of approximately 45%.
That is massively counterintuitive. You're telling me that if my single agent is relatively good, say 60% or 70% accurate at solving a problem, adding more agents actually makes the overall system statistically worse, slower, and more expensive. Why does competency punish collaboration?
It's a mechanism of trade-off between capability and coordination overhead. If an individual model is already highly capable, meaning it's solving more than 45% of tasks correctly, the marginal gain it gets from adding another agent is systematically less than the tax it pays to coordinate with them.
Okay, let's break down that tax. What exactly is being paid every time two agents talk?
It's expensive, token-consuming noise. Every inter-agent interaction requires the primary agent to generate tokens for communication, summarizing its state and asking for help. The receiving agent then has to spend tokens on context, parsing and integrating that new input into its own reasoning chain. This takes time, consumes the limited context window budget, and worst of all, it introduces information entropy.
Information entropy.
Right. When Agent A summarizes its complex work, all the edge cases, the discarded hypotheses, the nuanced symbolic reasoning for Agent B, it uses a kind of lossy compression to save on tokens and adhere to context limits. Semantic nuance is inevitably lost in that summary.
I see.
So if Agent A is already high-performing, the information lost in that required summary and the compute effort required by Agent B to process it often outweighs any small contribution Agent B might make. For highly performant models, say a hypothetical GPT-5, forcing them into a committee structure simply degrades performance because the coordination structure is nothing but expensive noise.
This directly leads to what the sources call the baseline paradox. The swarms are most effective when the models are individually weak.
Precisely. If you're stuck using a smaller, less capable model like a Llama 8B baseline, which might be only, say, 20% accurate, a swarm provides a significant necessary performance boost. The collective error correction strongly outweighs the coordination cost. The agents genuinely help each other past hurdles. But once your individual model reaches that 45% competency, the complexity of managing the communication starts dragging the whole system down. Architects must now benchmark their single-agent baseline first. If that baseline is 50%, scaling up is statistically proven to degrade performance while exponentially increasing cost.
That is a fundamental challenge to how large-scale AI projects are currently structured. But the risk goes beyond diminishing returns. It enters a realm of catastrophic failure, which brings us back to the systemic danger we introduced earlier, the infamous 17.2x error amplification.
This is the nightmare scenario the study validated. The telephone game effect taken to its computational extreme. This occurs specifically in independent agent topology systems, where agents operate in parallel or sequence without strict, centralized oversight or a validation layer. The core problem, again, is the viral propagation of hallucination.
Can you walk us through a specific failure chain to illustrate how that 17.2x amplification actually happens?
Yeah, let's use a mission-critical scenario: data migration and refactoring. We task Agent A with reading a legacy database schema and translating the required fields. We tell Agent B to write the new migration script based on Agent A's output. There is no shared verification state or manager agent checking Agent A's work against the original source of truth.
Okay, so they're just trusting each other.
They're trusting each other blindly. Agent A makes a subtle hallucination. Instead of reading the variable type decimal 18.2 for a pricing field, it misinterprets some verbose context and outputs the field type as a simple integer.
Oh, no.
Agent B receives this output. It doesn't question it. Agent B operates on the assumption of competence, treating that hallucination, the faulty data type, as ground truth.
It has no reason to assume Agent A failed, so the error is immediately inherited and sanctified by the next agent. It moves from a subtle error to a structural flaw.
Exactly. Agent B builds its entire migration script on the premise of integer pricing. Agent C, tasked with validating the post-migration data, encounters errors, but tries to use Agent B's script as the source of truth for troubleshooting, compounding the error further. Agent E, tasked with launching the new pricing service, is working with flawed data that strips away 2 decimal points.
And this is where the big number comes in.
This is where the statistical reality derived from the Google MIT study becomes terrifying. Independent, uncoordinated agents amplify these semantic errors 17.2 times faster than a single agent operating alone. The conclusion was stark. The output of an uncoordinated swarm of 10 agents passing context back and forth without supervision is statistically usually garbage.
17.2 times. That puts the fear of computation into you. It highlights that AI safety isn't just about preventing malicious intent. It's about containing basic, probabilistic screw-ups that multiply out of control due to architectural flaws.
It's a sheer information theory failure, exacerbated by these stochastic models. We mentioned context collapse and brevity bias. To save tokens, Agent A strips away the critical nuance and uncertainty, all the discarded hypotheses, the RE 0.95 probability marker, and presents a concise, confident, but flawed output to Agent B.
And Agent B just takes it as fact.
Agent B receives this compressed summary as a definitive factual statement, completely lacking the thought process or doubt that led to it. It takes the token with the highest log probability as absolute truth.
So if we accept that an independent democracy in an AI swarm is a disaster because of this 17.2x amplification, what is the architectural mitigation strategy?
The answer lies entirely in topology. The research contrasted the catastrophic failure rate of the independent swarm, the 17.2x amplification, with a much safer centralized coordination model, which they sometimes refer to as a dictatorship topology.
A dictatorship, okay.
In this model, we introduce a designated boss or manager agent. This manager agent reviews worker outputs and acts as a strict validation gate. Going back to our financial example, the manager agent checks Agent A's hallucinated revenue figure against the original source documents, the ground truth, before Agent B is allowed to calculate the profit margin.
So it contains the error spread immediately?
It contains it right away.
And how effective is this containment strategy? What does the number look like?
Centralized architectures were found to contain error amplification to a much more manageable 4.4x.
Okay, that's a huge improvement.
It is. While that is still amplification, you haven't solved the underlying probabilistic nature of the LLM. It's a massive quantifiable reduction from 17.2x. This makes the system predictable, safer, and mathematically contained.
What's the inherent trade-off of running a dictatorship model? There has to be one.
Latency and a single point of failure. The boss agent becomes a central latency choke point because every single output must pass through it for validation. And if the boss agent fails, the entire system halts. However, the study's conclusion remains firm. For accuracy-critical applications like finance, medicine, or code deployment, democracy doesn't work for AI swarms. Centralized dictatorship does.
We also need to talk about task types. It sounds like the effectiveness of scaling agents is entirely dependent on whether the problem can be broken down easily or if it requires deep sequential dependence.
Absolutely. This is the task-contingent performance finding, which found a stark dichotomy. Let's start with the bad news, the sequential penalty. For tasks requiring tight, step-by-step reasoning like complex software refactoring or sophisticated multi-stage data analysis, performance dropped significantly. We're talking drops ranging from 39% to 70% when distributed across multiple agents.
70%? Why such a severe drop? Why can't the agents just pass the work along?
The penalty is caused by context fragmentation. In a sequential task, the state of step n is critically dependent not just on the output of step n1, but on the full thought process and reasoning that led to that output. When different agents handle these steps, the full context of that thought process is lost. Agent B sees the summary output of Agent A, but not the discarded hypotheses or the reasoning path that led to the final output. This leads to logical discontinuities, gaps in knowledge, and massive drops in the final code or analysis quality.
Conversely, what about tasks that are naturally parallelizable, where we can divide and conquer?
That's the parallel advantage. Tasks that can be cleanly decomposed into independent, non-communicating units, such as analyzing thousands of customer tickets for sentiment or performing compliance checks across thousands of unique regulatory documents, saw huge performance gains.
Oh, huge.
With proper multi-agent coordination, they saw improvements up to 80.9%. In these cases, the agents only communicate with the central aggregator at the very end, which minimizes that coordination tax and maximizes throughput.
The token efficiency beta ties this all together by providing a clear financial consequence for poor architecture. You are literally paying heavily for failure.
The data is damning. The study tracked how many tasks could be completed per 1,000 tokens consumed. Single agents operating efficiently achieved an impressive 67 tasks per 1,000 tokens. The independent swarms, the ones amplifying errors by 17.2x, were wildly inefficient. They required far more tokens to communicate and iterate, and only achieved 21 tasks per 1,000 tokens.
So you are paying 3 times the compute cost for a system that is statistically likely to produce garbage output 17 times faster.
Exactly. It creates an unassailable financial case against blind scaling and uncoordinated agent architectures.
So we've established that the risks are geometric, the performance is contingent on this 45% baseline threshold, and the failure amplification is severe at 17.2x. The old way of doing things, that artistic, fragile, ad hoc tweaking we call prompt engineering, is clearly inadequate to manage this level of systemic risk. We need a new discipline entirely.
We must immediately recognize the death of prompt engineering. That was the craft of whispering to a static oracle, tweaking formatting and adjectives to coax a better response. It was fragile, non-deterministic, and frankly, unscalable beyond a single contained interaction. Agentic engineering is the necessary, rigorous shift required to move beyond what early developers called vibe coding.
Vibe coding. I like that. So what is the primary focus of agentic engineering that distinguishes it from its predecessor?
Agentic engineering is a rigorous discipline that focuses on system-level problems and component reliability. It treats the agent not as a black box, but as a component in a larger verifiable machine. Its core concerns include state management, how memory is persisted, verified, and structured,
Right.
tooling interfaces, how APIs are rigorously typed and securely guarded, observability, how the agent's thought process is traced and audited, and critically, control flow, how loops, recursions, and retries are mathematically bounded to prevent those massive resource spikes we discussed.
The sources introduce a highly structured solution to enforce this rigor, the SPARC framework. Let's dedicate some time to this, as it seems to be the new gold standard for reliable autonomous systems.
SPARC stands for Specification, Pseudocode, Architecture, Refinement, and Completion. It's popularized by organizations like the Agentic Foundation, and it transforms these vague, high-level instructions into a rigorous, verifiable transition pipeline designed specifically to mitigate that geometric risk.
Okay, let's start with S, specification. This is more than just stating the goal.
Oh, much more. This is the contract creation phase. The agent, or the human overseeing the agent, creates a comprehensive requirements document. It defines the specific objectives, user scenarios, failure modes, functional requirements, what it must do, and non-functional requirements, like how fast, how securely, how efficiently it must do it.
I see.
And crucially, the sources mention an advanced analysis here called complexity assessment. This ensures the problem is mathematically solvable within the agent's allocated token budget and time constraints before any costly execution begins.
So it's a sanity check.
It's a sanity check. If the problem requires more reasoning steps than the LLM's context window can hold, SPARC ensures the system flags it during specification, saving huge costs and preventing that inevitable context fragmentation later on.
Then we move to P, pseudocode. Why is this intermediate planning step so vital before the agent starts writing any real code?
It forces the agent to think before it speaks or acts. Before writing a single line of runnable, executable code or mutating any database, the agent generates a high-level logic roadmap. This provides a low-cost, low-risk stage for what we call logic verification.
So a human can check it.
A human or another system can review the pseudocode to ensure it adheres to essential safety constraints. For example, explicitly checking for and correcting the dreaded infinite loops in the retry logic that we see in those resource spike incidents. If you catch a logical error here, you save an incredibly expensive high-risk execution cycle later on.
And A, architecture. This seems designed specifically to counteract that tunnel vision that LLMs often suffer from when they're given a code task.
That's precisely right. LLMs, when simply prompted to write code, often generate these isolated, disjointed files without considering the larger system context. The architecture step forces the agent to explicitly define the system components, the technology stack, and the data flow across those components.
So it sees the whole picture.
By forcing the agent to explicitly see the entire system before focusing on individual files, you prevent disjointed, high-risk code, you minimize unnecessary dependency bloat, and you ensure every component selection is justified.
Next is R, refinement, which is the core iterative loop.
This is the critical self-correction and optimization phase. The agent critiques its own design against the initial specification, and it actively uses symbolic reasoning to optimize its algorithms. This is where the agent moves beyond just working to becoming efficient.
Okay, give me an example.
For instance, in refinement, the agent might identify an algorithmic inefficiency. Say, its current solution for sorting or comparing customer records is operating at O(n) complexity. This means if you double the number of customers, n, the computation cost increases fourfold. Right.
The agent then optimizes it to a faster, more scalable O(n) solution, where doubling the customers only doubles the cost. In practical terms, this can mean the difference between paying a few $100s for tokens versus saving $100,000 in monthly token costs for an enterprise-scale task.
And finally, C, completion.
This is the verified transition point. The code is only considered complete when it passes the extensive suite of unit, integration, and system tests that were required and specified back in the initial specification phase. By injecting these rigorous validation checks at every state transition, SPARC provides a robust defense against that geometric error propagation. Errors are caught and fixed at the planning stage, which is cheap, rather than propagating to execution, which is expensive, risky, and leads to the 17.2x amplification. SPAR deals with the structure of the task, but agents also need sophisticated memory management to prevent that context fragmentation we talked about. That leads us to Agentic Context Engineering, ACE.
ACE is the necessary complement to SPARC. Traditional context management was essentially a linear log. User said X, AI said Y. Here's the history of the past 50 interactions. ACE treats context as an evolving playbook or a dynamic knowledge base.
Okay.
Instead of just dumping tokens into a linear chat history log, the system maintains a structured, dynamic state object, often a standardized JSON object, that actively tracks the current goal, completed steps, known facts, which must be verified, ground truths, and pending questions.
That seems much more robust than relying on the LLM to fish through a massive, unstructured chat history.
It creates signal, not noise. ACE requires active context pruning. It intelligently removes irrelevant history and transient thoughts that are no longer necessary for the current step. This prevents context collapse, ensuring the agent's attention mechanism remains focused strictly on the most critical signal it needs to achieve the current specific goal, rather than getting distracted or confused by noise from 5 steps or 5 hours ago. This rigor in memory management is crucial for those sequential tasks that we know are penalized so heavily by context fragmentation.
Agentic engineering and the SPARC framework give us structural rigor, but for safety-critical systems, I'm thinking medical triage, autonomous trading, infrastructure deployment rigor is not enough. We need mathematical certainty. We need to move beyond probabilistic good enough to verifiable fact.
That's the consensus across highly regulated industries. For financial market stability or human safety, you cannot simply hope that a system will eventually converge to a correct solution. This is why the field has been pushing heavily toward formal verification methods integrated directly with LLMs. Formal methods attempt to prove mathematically that a piece of software meets its specification under all possible conditions.
The problem, as we've discussed, is that the LLM-verifier refinement loop is notoriously unpredictable.
It acts like a black box of uncertainty. The verification loop, where the LLM generates code, the formal verifier finds a bug, and the LLM attempts to fix it, can exhibit highly problematic behavior. It can oscillate, meaning fixing bug A inadvertently breaks bug B, sending it into an endless cycle.
And it could just run forever.
Worse, it can diverge completely, making resource planning impossible. Engineers couldn't predict if a system would ever converge to a correct, verified solution, or if it would simply burn through thousands of dollars worth of tokens trying to fix a single misplaced semicolon before timing out.
So the goal was to model this process mathematically and turn uncertainty into a predictable, calculable resource cost. This is where the breakthrough paper from late 2025 comes in, the $4 delta convergence bound theorem.
This theorem is transformative because it provides a mechanism for budgeting for certainty. It models the LLM-verifier interaction as a sequential absorbing Markov chain. Now, that sounds dense, but the concept is actually pretty understandable if we use an analogy.
Please do.
Imagine the verification pipeline as a journey up a complex, multi-stage staircase. Each step represents a verification stage, compiling the code, running a test suite, synthesizing invariants, or performing an SMT check. The system's objective is to reach the top of the staircase, the verified state. In Markov chain theory, once you reach the verified state, it's an absorbing state. You stay there, the job is done.
Okay, so the agent keeps attempting transitions step by step until it hits that final verified state. We need to define the critical variable here, delta. What is delta?
Delta is defined as the error reduction probability. It is the likelihood that a specific verification stage will move the system closer to the verified absorbing state in one single step. Essentially, delta is a rigorous measure of the agent's effectiveness at self-correction on a given task.
So a high delta means it's good at fixing its mistakes.
If delta is high, the agent is highly competent and moves up the stairs quickly. If delta is low, the agent is clumsy, spending many steps correcting itself just to stay in the same place.
And the theorem translates this effectiveness probability, this delta, into a reliable resource cost, which is the expected number of iterations and required to complete the task.
Precisely. The formula states, the expected value of n is less than or equal to 4 divided by delta dollars. This formula provides a reliable worst-case ceiling for the expected number of iterations required to reach convergence. It converts the verification process from a probabilistic hope into a calculable certainty. You no longer have to budget for an infinite loop, you budget for $4 delta.
And what's also important is that this wasn't just theoretical math. The sources note this bound was empirically proven across massive amounts of data.
That's what makes it an engineering tool, not just a theoretical concept. Across 90,000 verification trials, the research validated the bound, showing 100% convergence for all systems where delta was greater than 0. The empirical results match the theory with striking consistency, confirming that the $4 delta bound is a universally reliable tool for resource planning and budgeting.
So how does this actionable knowledge look in practice? How do engineers use their measured delta to determine if an agent is safe and cost-effective enough to deploy?
They use it to define clear engineering operating zones. By running initial benchmarks, engineers calculate their agent's delta and map it directly to the expected convergence time. The sources define 3 zones based on this parameter, using 4 divided by the delta value to calculate the expected maximum number of steps.
Okay, what's the first one?
First, the high-performance zone. This is where delta is greater than 0.6. If your delta is, say, 0.65, then 4 divided by 0.65 means convergence is expected in fewer than 7 steps. This zone is fast and highly reliable. It's ideal for safety-critical, high-throughput applications like autonomous high-frequency trading or immediate infrastructure deployment where time and correctness are paramount.
Then we have the standard business use case, the practical zone.
That's defined by a delta between 0.3 and 0.6. The expected iterations fall between 7 and 13 steps. This is the sweet spot for standard enterprise tasks, routine coding, data manipulation, standard content generation, and structured audit tasks. It offers the optimal balance of performance, cost, and guaranteed convergence time.
So if the practical zone is our sweet spot, what does the math tell us about when we absolutely must pull the plug and refactor? That brings us to the danger zone, the marginal zone.
The marginal zone is defined by any delta less than 0.3. If an engineer measures their agent's delta at, say, 0.2, the maximum expected iteration count is 4 divided by 0.2, which is 20 steps. Systems operating here are considered unsafe for production because they have high latency, massively high token cost, and a significant risk of timeout or resource depletion.
That's just not viable.
It's not tenable. The $4 delta bound allows them to shift resources or refactor the prompt immediately, replacing the old, expensive wait-and-see development strategy with a rigorous calculate and provision model.
We established the math of the failure cascade, that 17.2x amplification, and the math of the solution, the $4 delta bound. Now, we need to move to the architectural safeguards necessary to contain these geometric risks in real time. If the agent starts running away, calculating too many steps, or amplifying an error, how do we pull the plug? This is the realm of governance.
This is where we introduce the circuit breaker mandate. Just as an electrical circuit breaker prevents a power surge from melting the wiring, an AI circuit breaker must detect anomalous or malicious behavior and sever the connection before the damage cascades across the system. Both NIST and Gartner have released guidance explicitly recommending their mandatory use.
Let's focus on the formal guidance from NIST because it makes the mandate crystal clear.
NIST Special Publication 800-228, Under Control, RISC API 16. Circuit Breaking and Resilience mandates this mechanism for API protection. The standard requires organizations to set specific thresholds on request concurrency and implement fail-safe mechanisms to protect back-end APIs from being overloaded or failed by autonomous agents.
This is a crucial distinction we need to stress for the listener. A circuit breaker is fundamentally different from a simple rate limit.
Oh, absolutely. A simple rate limit merely slows down a misbehaving agent. It's a throttle designed to manage legitimate load. A circuit breaker stops it completely. If an agent fails 5 times in a row, or if its request velocity suddenly spikes, the breaker trips or opens, severing the connection. All subsequent requests from that agent fail fast without ever hitting the back-end service. This prevents the thundering herd problem, where a swarm of agents attempts to retry a faulty operation simultaneously and brings down the entire service layer through sheer volume of failure.
What are the key environmental triggers that should cause this breaker to trip?
The guidance lists 3 critical risk indicators that must be monitored. The first is resource spikes, where an agent starts consuming tokens, CPU, or API calls, far exceeding the standard deviation for its defined task. For example, if a payment agent accidentally enters an infinite while true loop, attempting to retry a faulty connection. Second is error rate thresholds. This is the mechanism designed specifically to detect the operational manifestation of that 17.2x telephone game effect. If the agent chain's self-reported confidence scores drop below a certain point, or if the rate of system errors rapidly accelerates without human input, the breaker trips to halt the cascade before that semantic drift causes catastrophic, silent damage. Third, and perhaps most subtle and security critical, is goal drift. This occurs when an agent attempts to access resources outside its defined, authorized security bounding box. If a marketing analytics agent suddenly tries to query HR salary records, or a simple content generation agent tries to initiate a database migration, it is displaying anomalous, unauthorized behavior. The circuit must open immediately.
And since these agents operate at machine speed, human intervention is impossible. We need immediate machine-driven interruption protocols and kill switches.
The necessary framework emphasizes hard-coded, privileged override APIs. A human cannot physically intervene fast enough to halt a rogue swarm that's executing hundreds of transactions per second. You need an immediate API-driven suspension of the agent's execution environment.
And a plan for what happens next.
Furthermore, organizations must have predefined mitigation playbooks that automatically trigger when a breaker trips. Incident response must move from reactive panic to procedural containment. The trip should immediately freeze the agent's full state for forensic analysis and alert the specialized agent ops team.
Now let's talk security, because the scale of this problem is shifting identity management. The sources emphasize that agents are not just sophisticated scripts, they are non-human identities, NHIs, and they are quickly starting to dominate enterprise interactions.
That's a massive security shift. NHIs now outnumber human identities in many large enterprises by ratios up to 100-to-1. They can adapt, persist, and potentially be subverted. Security must radically shift from a simple trust-based model, we trust this agent because an admin deployed it, to a comprehensive zero-trust, verified transition framework.
What does zero trust demand in the specific context of an autonomous agent?
It demands radical scrutiny and least privilege. Every agent must possess a unique, cryptographically verifiable identity. When Agent A requests data from Agent B must verify Agent A's identity and its current authorization scope every single time. Agents must operate under the strictest possible least privilege.
So no God mode agents?
No. If an agent is tasked with a read-only analysis task, it must cryptographically lack the ability to execute any write, delete, or elevate privilege operation. Its tokens must only grant it the minimum necessary access.
This focus on privilege is absolutely vital in defending against the highest risk vulnerabilities cited by OWASP, excessive agency.
Excessive agency is OWASP Top 10, number 6, and it's a direct consequence of lax permissioning. This occurs when an agent is granted more permissions than it strictly needs to complete its task. The risk is extreme because if an attacker successfully injects a malicious prompt, a sophisticated context-aware command into a superuser agent, they immediately inherit that agent's broad permissions.
Wow.
The agent then becomes a perfect insider threat, exfiltrating massive amounts of data or modifying core systems while appearing to be a perfectly legitimate, authorized internal process. Traditional security tools that look for malware signatures or unauthorized IPs will miss these attacks entirely, as the agent is technically an authorized user.
So how do we counter that kind of sophisticated, context-aware prompt injection attack?
We need defense in depth, specifically tailored to LLM risks. One mandatory solution highlighted by the guidance is a dual LLM architecture. This involves using a separate, often smaller, and highly optimized guardrail LLM to scan the primary agent's inputs and outputs for malicious signatures, goal deviation, or sensitive data leakage before allowing the primary agent to execute any API call.
So it's like a prefrontal cortex.
It acts like a prefrontal cortex, checking the primary agent's potentially malicious or runaway impulses before they become action. Additionally, the foundation of forensic accountability is required. Maintaining comprehensive immutable audit logs of all agent decisions, all tool calls, and the agent's internal thought processes is crucial, both for regulatory compliance and, most importantly, for the forensic reconstruction of the inevitable failure chain. If a catastrophic error occurs, we need those logs to trace the semantic drift back to the original probabilistic screw-up that initiated the 17.2x amplification.
So what does this all mean for the learner? We've taken a deep dive into the engineering rigor required to survive the age of agentic AI, moving from the probabilistic hope of prompt engineering to the mathematical certainty of agentic engineering.
The three major actionable lessons for any organization adopting this technology are clear and they're quantitative. First, you must benchmark your baseline performance and scale only when that baseline is below the 45% threshold. Scaling up competence often leads to worse outcomes due to that geometric coordination tax and information entropy.
Second, the architecture matters profoundly because failure scales geometrically. For high accuracy, safety-critical tasks, you must employ a centralized, hierarchical dictator topology to contain error propagation. This reduces the crippling 17.2x error amplification seen in independent swarms down to a much more manageable 4.4x.
And third, you must enforce a new level of rigor at the systems level. Adopt Agentic Engineering, specifically the SPARC framework, to move beyond fragile vibe coding and architect your systems with zero-trust security. You have to ensure every non-human identity operates with least privilege and is protected by mandatory circuit breakers as dictated by NIST Reg API 16.
The conclusion here is powerful. The value of AI is rapidly moving away from the sheer size and capability of the monolithic model and entirely toward the rigor, predictability, and safety of the system design. Predictable, secure, and mathematically sound systems are the new gold standard in AI deployment.
And we end where we found the ultimate mathematical breakthrough, the $4 they call it Convergence Bound. This knowledge fundamentally allows us to budget the exact tokens, time, and resources needed to guarantee an AI system's correctness and convergence. It converts certainty from a philosophical goal into an engineering calculation.
So here's the final provocative thought for you to chew on. If we can mathematically model and calculate the resources needed to guarantee that a safety-critical agent, be it a medical diagnostic tool, a traffic control system, or a trading algorithm, will converge to a correct solution, what are the ethical and legal implications of deploying that agent without first completing that convergence calculation? Thank you for joining us for this deep dive. We will catch you next time.